The movie you're about to watch is a presentation of some results obtained by a group of first-year students at Roskilde University. They studied water balloons bouncing off a bed of nails. And then they recorded this by high-speed recording. Now you may wonder, why did they do that? Well, at the end of the movie we'll show some of the scientific background, but first let's show some of their recordings. We start out by showing the bounce of a conventional ball. So when the ball impacts on the surface, it compresses slightly, like a spring. Some of the kinetic energy is stored and then released again, accelerating the ball in the upwards direction. Now let's look at how a water balloon bounces off a surface. As you can see, the water balloon deforms completely on impact, then it retracts again and then jumps off the surface. When we look at a water balloon bouncing off the bed of nails, it again completely deforms, but in this case some of the material penetrates into the nail pattern. And much like a jump on a trampoline, this material will recoil back and lift the water balloon off the surface in the pancake shape before it has time to retract. So this is the famous pancake bounce. Now let's look and compare the two water balloon movies again. So the inspiration of this work was some recently published research results. In June 2014, a paper came out in Nature Physics by Professor Julia Yeomans and co-workers. The title of the paper is Pancake Bouncing on Superhydrophobic Surfaces. Hydrophobic means water repelling, and superhydrophobic then means extremely water repelling. They studied the bounce of water droplets. So when a water droplet hits a hydrophobic surface, it will bounce like a ball. But if you then add some microstructure to this hydrophobic surface, then under the right conditions, it will bounce off in the pancake shape, like we saw with the water balloon. The interesting implication of this is, compared to the conventional bouncing, the pancake bounce has a contact time that's reduced by a factor of 4 or 5. In the scaling of the problem, one dimensionless number that is conserved is the Weber number. The Weber number is the ratio of density times radius of the droplet times velocity squared to the surface tension. So this number tells us something about the ratio of kinetic energy to surface energy. Another number that may be important for this problem is the Reynolds number. The Reynolds number is the ratio of density times characteristic length times streaming velocity divided by the kinetic viscosity. So this number tells us something about the ratio of inertial forces to viscous forces. In our case, the scaled up version, the Reynolds number is increased by a factor of 5,000. So this tells us that apparently the Reynolds number is not important for this problem. So hopefully the fact that we can scale the pancake bouncing to a much larger scale tells us something about the physics of the pancake bouncing phenomenon.